Okay.
Thank you.
Yep. Actually, I think this is a good point to bring in my talk because we had performance portability between GPUs. Now I'm going to talk about performance portability between Xeon Phi and traditional Xeon architectures on the CPU side of things. To do this, as mentioned, I'm going to talk about the acoustic wave equation example. I think it's very relevant to this audience. But also many of the tuning strategies for the acoustic wave equation are relevant in other contexts as well. So many of the things I talk about here will carry over to many other kinds of applications. Specifically, I want to kind of emphasize how many of the tuning strategies that apply very well on Xeon Phi architecture tend to port very well on traditional Xeons as well. And one of the things that's kind of enabled this to happen is advancements in hardware, but also advancements in software stacks and compiler infrastructures. Just as a kind of overview, I'll just give you the basic kernel. I stuck to a very simple one because it fit on one slide. I talk about how to use some relatively new features of OpenMP to enable vectorization of the kernel. I'll talk about how to block for cache efficiency, how to use OpenMP tasks, which are not quite as new as vectorization, but still kind of new. And finally, I'll get into MCD-RAM considerations, which is more relevant on Xeon Phi than on Xeon, but I still think can be incorporated in a very portable way. Here's the basic kernel. Many of you, this is not a big surprise. You loop over all of the grid points, and at each grid point, you compute your whatever stencil you're working on. I've parameterized over order here, and I have a coefficients in a header file. It's a very big file. But the orders I'm thinking of are kind of higher orders because that increases the arithmetic intensity and makes it more interesting on Xeon Phi. Time limits, I'm just going to assume that we can parallelize this already. I'm just going to focus on how do we get best per core performance once we have, assuming already having parallelized this. So moving into this, on the top I have kind of a stripped down kernel where I'm only focusing on the parts that I'm going to change. So I've removed the top level loops and I've only have the inner loops. One thing that's kind of problematic in the finite difference kernel on the stencil side is that in two of your dimensions, if this is three-dimensional, you have strided memory access, which is not ideal, especially if you have very large vector units as you do in Xeon Phi architecture. So I'm going to interchange those loops and put in the nice Pragma OMP SIMD, which indicates to the compiler that this can be safely vectorized. And I'm kind of taking a leap of faith that it will be right. But I happen to know it's right because I've done this already. And I threw in there another feature from OpenMP. So the vectorization with OpenMP comes with a lot of features to help with performance. One of those things is the alignment directive. I can say that the pointers are aligned. Previously, you have to use a lot of compiler-specific stuff or lots of things that don't port well, and then you have all these preprocessor statements saying, okay, well, if I'm in GCC, do this. If I'm in Intel, do this. If I'm in Cray, do this. But you don't have to do that anymore, at least with vectorization. So I just put that there to say that that's an element of how we can have performance portability. And I've parameterized the alignment because maybe that will change. But since the theme is performance portability, and I just made a change to make better vectorization, I have to now argue that that was a good change everywhere. And it turns out that is almost always an ideal change. You almost always want unit stride access, regardless if you're on Xeon Phi or not. I mean, if you're on Xeon, and if you're on an older Xeon with a smaller vector unit, that still gives you the best cache access. So it's almost always a change you want to make. So that is a portable tuning that you almost always have to do. Speaking of cache, the code as it is doesn't make the best use of cache, and we can remedy that by adding in some blocking parameters. At the top is the unmodified kernel. I just stripped out everything that's non-essential. And then I added these block I, block J, block K parameters. The idea being that instead of looping over each grid point, I loop over blocks, and inside the sub-blocks I do my computation. Hopefully the block parameters are picked so that the sub-blocks fit inside whatever cache we're working with. And bringing back the performance portability, this is also a portable transformation. Just the difference is blocking parameters will change. But you always have to do this. You never don't have to do this. So I mean, it's picking the right blocking parameters can be a hard problem, but you always have to do it. So far, all the changes I made work well on Xeon and Xeon Phi. And now that I've tuned for data locality, another thing that comes up, especially on Xeon Phi, is hyperthreading. And on traditional Xeon architectures, you don't necessarily want to hyperthread. But on Xeon Phi, you can't ignore it. Hyperthreading usually kicks in when you have some kind of data dependency, and one of the core is sitting there cycling, waiting for data to come in. It can spin up another hyperthread, and it can start doing work. But the catch is the data has to be there for that hyperthread to do work. Otherwise, it will just sit there too, and neither of them are doing anything. So now that I've blocked for cache efficiency, I kind of already have encoded in my kernel that locality I need so that if a hyperthread does come up, it has data there. And I found through my experiments that actually using OpenMP tasks is a very useful way to exploit this. So I have the blocked loop, and I've kind of removed the inner loops again just to make this all fit on one slide. And all I've done is said pragma OMP task on the innermost part of this. And what that does is say, well, this subblock can be executed asynchronously. And I've actually found that as long as you get the thread affinities right, this will spawn up the hyperthreads and get you the nice efficiency boost on Xeon Phis. And on Xeons where you don't want hyperthreading, just turn it off and it executes sequentially, no problem. So this is also a portable code transformation. And it almost always helps on Xeon Phi. If it doesn't, just turn it off. And kind of changing gears from data locality, I'm going to talk about MCD RAM, which is a very Xeon Phi specific thing at the moment, but I believe it's here to stay. And I don't have a code slide for this one because MCD RAM usage usually doesn't change the kernel, it changes how you use the kernel. If you have a Knight's Landing in cache mode, and that means that the MCD RAM is acting as a extra cache layer, that's happening transparently to the code. So you don't need to make any code changes. The way it usually comes out is you'll have to change the blocking parameters to account for the fact that you have different latency characteristics dealing with that. On flat mode, you have to manually manage that MCD RAM. But what I found is, with finite difference kernels and other kind of kernels, you end up keeping the kernel exactly the same, but how you call it is different. Since MCD RAM is limited, you will allocate some kind of staging array and feed in your grid chunk by chunk until you're done. So I don't have a code slide for this because, again, the kernel doesn't change. But different parameters might apply in that situation. So this didn't really happen in a vacuum because all of this stuff I did to make this very portable wasn't always possible. Looking at previous generation Xeon Phis, it was a little bit harder to achieve this kind of portability, but also a lot of the OpenMP infrastructure wasn't always supported by all compilers, or it didn't exist. So vectorization is a big example of that. Doing lots of other things like doing thread affinity with OpenMP, which I do all the time. Doing collapsing, which, sorry I didn't mention it earlier, but if you pick your block parameters and they're too big, what if that's not enough parallelism? Well, you have 68 cores to work with on Knight's Landing. On Xeon, that may not be a problem. Well, OpenMP gives you a very nice, transparent way to give yourself extra parallelism. Using different kinds of scheduling. So on Knight's Landing, maybe schedule that you want. It's not the same as the schedule you want on a Haswell. And using tasks has given me, so far, a very effective way to utilize hyperthreading in a portable way across Xeon and Xeon Phi. This is a list of all the parameters that came out of just this simple code. Actually, there's a lot of extra stuff that ends up going into a final product. These are just some big picture examples. I'll usually put these in a header file somewhere and with preprocessor statements saying, okay, well, if I'm compiling with AVX 512, do this. If I'm just to get all the right parameters, and those have to be picked by an expert or brute forced, auto-tuned, however you do it. So I used this kernel. So I actually did two experiments. The first experiment was just doing everything I showed in the slide. On Knight's Landing, I was about to get about 5 billion grid points per second. On a dual socket Haswell, about 4 billion grid points per second. This is on a 16th order finite difference stencil. I'd like to note that on Haswell, that's basically peak. If you do a roofline analysis, you can't really do any better than that on this particular stencil. But I thought I could do a little better than that on Knight's Landing, so I added in a few extra tuning parameters, and I brute forced over those. And I was able to get about 8 billion grid points per second. Again, Haswell was at the peak, so I didn't do any better, even with the extra parameters. And I did this on a dual socket Haswell machine so that the power usage was comparable. Otherwise, it would be half of a KNL. So I didn't think it would be a really good comparison then. So I hope the takeaway for all of you is that we are at a point, at least with Xeon and Xeon Phi, that performance can be done in a very portable way. And I'm doing it every day now. This is just one example, and I did achieve it there. This really helps keep your code base under control, and I think it helps make the code a little more readable and understandable without having all these different cases that everyone have to read through. And it doesn't have to sacrifice performance. And I only really scratched the surface here. I showed some really big stuff that really get good performance, but there's the last 20-30% of performance that I didn't talk about, and I believe a lot of that can be done in a very portable way also. Just as a quick pitch, in about a month from now, at Rice, I'll be giving a free Knight's Landing tutorial. It's a 2-day course, 8 hours a day, and if you really want to get good in-depth coverage of these tuning strategies on Knight's Landing, feel free to take a picture, write down that link. And there's a registration form online now. So this was just confirmed yesterday, so the registration form is a little bit lacking on information, but it has the form for you to fill out, and we'll get information from you. And that's it for now. Thank you.
As you made these optimization steps for the Xeon 5 and tried to do the same thing for Xeon as well, did you notice an improvement in Xeon performance? Said another way, did the gap between the Xeon and Xeon Phi reduce in terms of performance improvement?
If I let me repeat and see if I understand. You're asking if tuning a code for Xeon Phi, did I see improvements on Xeon having made those changes? Yeah, that's actually pretty common. I do find frequently that if I'm taking a code originally written on Xeon and I port it to Xeon Phi, tune it, if I rerun it on Xeon, it's faster than it was before, simply because Xeon Phi forces you to make a lot of tuning choices that are optimal also for Xeon. But you can kind of get away with not because, cache sizes are bigger, it's a little more forgiving, and so forth. Does that answer your question? Yeah.
Have you had any experience with IBM's compiler for OpenMP that's generating code for NVIDIA GPUs?
Only indirectly. So the question, you have the microphone, everyone heard you. I hope to get experience with that coming up, and I'm actually very excited about that. I think it's a very promising direction.
I'm just curious whether you think that the optimizations that you made for the Xeon Phi would be appropriate for running on a GPU, whether your OpenMP is really performance portable.
I think it could be, but the real question is whether the compilers will be ready for it. Because if you look at a lot of, for example, unit stride memory access on Xeon Phi, that goes by another name on GPUs, coalesced memory access. And you usually want to do that, depending on the application. So that is an optimization that ports over to GPUs, but it doesn't because GPUs don't understand OpenMP. So it doesn't really port, but conceptually it ports. I could think of how I would write a CUDA kernel using this OpenMP code and get the same performance characteristics by doing that optimization. The other tuning strategies, if they're not relevant on GPU, you can turn them off. Cache blocking would come in when you're using shared memory. That's a little more manual, though. So I think it's doable, but the programming model is not exactly there yet.
What version of OpenMP is this, 4.5 or and
Everything
also,
here works on 4.0.
Okay.
But if this is encourage anyone to look at OpenMP, I encourage you to look at 4.5 because
Right.
they've added a lot of stuff to vectorization that has made it a lot more usable.
And what version of the compiler?
So this one was Intel 16 something. I can't remember the exact subversion. Works on GCC as well. And I can't remember. I tried some other ones as well, but those results were Intel compiler.
I have a question. This looks pretty impressive. Well, are we done now? I mean, does that solve the problem of code portability between Xeon and Xeon Phi and potential other, at least similar enough architectures in the future? Or another way phrased, where's the catch?
Well, I mean, you can always chase after the last 10% of performance, forever, and you'll never be done. And as mentioned, brought up by this great question over here, getting this onto GPU is also an open question. That's not quite there too. And I've actually worked with the programming model ACA, which was introduced in the last talk. That's one way of looking at it. I like OpenMP because a lot of people understand OpenMP. So when I'm teaching people how to program on Knight's Landing, it's really easy for me to get them started. So that's kind of the direction I'm going right now. But I mean, there's many ways to go.
Or if I may add on to that, what do you see the limits of this approach? Not to find holes in your story, but I'm trying to get a sense for how far does that take us, this approach?
Well, I don't know. I've had a lot of success doing this right now. I mean, you can always go in and do inline assembly. That's the limitation, really. I mean, you can always do that. And you can't, if you want this portability, you can't. But I don't see any reason why you shouldn't start out this way at least. At least get something going that works on a lot of places. And if you really want to tune beyond that, that's your starting point.
Got one more question. Could you characterize the performance improvement you achieved with this approach?
I didn't hear you, I'm sorry.
Could you characterize the performance improvement you got between Xeon and Xeon 5 in terms of how much improvement you saw?
It usually follows along the line of the specs. So if I'm on a bandwidth-bound problem, I get about 4 times faster on Knight's Landing because it's about 4 times the bandwidth of a dual-socket Xeon. If it's a compute-bound problem, I might see a little bit more than that. That's somewhere in between 1x and that, but usually more than 1x. I mean, 2x is pretty typical without doing too much work. Pushing that to 3x is doable. Going beyond that to 4x, it takes a little bit more work. That's usually what I see. It depends how much work you're willing to put into it. I haven't actually used OpenACC on Xeon Phis, so I can't really comment on that too much. I've used them a little bit with GPUs, and that was a long time ago. So I think it would be unfair to comment on that, because I know they've made a lot of improvements to it over the years. Yeah.